In this video, let's take a look at the calculation for a one-sample hypothesis test for the mean when the variance is known and we're using a two-tailed test. In this example, we're looking to increase the sales of a product. So the marketing team has launched a new campaign. Historically, the average price was $72.83. Using hypothesis testing, we're going to determine if the marketing campaign has changed the average purchase based on a 0.05 level of significance. So we know this is a two-tailed test because we're looking to see if it's changed. It could have increased the average purchase price or decreased the average purchase price. So using all of the sales information since the launch of the marketing campaign, we can calculate a mean of $74.29 and a standard deviation of 39.56. So here we know that the variance is known because we're using all of the data. So we know all of the information about the population. In this case, our N, or our sample size, was 3,619 because it was all of the sales information since the launch of the campaign. So since we're using a two-tailed hypothesis test, we're going to set our null hypothesis that the mean is equal to mu naught. The alternative hypothesis then would be the opposite, that the mean is not equal to mu naught. Given the information that we have so far, we know that mu naught is $72.83. Our x bar is $74.29. Our standard deviation was 39.56, and our sample size was all of the purchases since the launch of the marketing campaign, which was 3,619. We're using a two-tailed hypothesis test, so we're going to look at both sides of the distribution. So we'll have a positive z-value and a negative z-value. From the positive side, we have a value of 1.96, which equates to our 0.05. And then on the left-hand side, we would have the negative 1.96. We can calculate then our z-value based on our x bar from cell B21 minus mu naught from cell B20 divided by the standard deviation from cell B22, which is divided by the square root of our sample size in cell B23. In this instance, we have a z calculation value of 2.220. When we look at where the 2.220 falls, it is to the right of the positive z-value of 1.96. Therefore, we're going to reject our null hypothesis. So we can set this up through our logic that if we'll have to have our B27, which is our z calculation, is greater than B25, which is our negative z-value, and we've got our B27 value, which again is our z calculation, is less than B24. So this is looking to see if the value falls in the do not reject region. So if it's greater than the negative z-value or less than the positive z-value, and it has to be both, then we're going to fail to reject the null hypothesis. Otherwise, it would not be in this region, so we would reject the null hypothesis because it would fall into one of those two regions. In this case, we are rejecting it, so our conclusion from our logic is to reject the null hypothesis that the mu is equal to mu naught. We can also calculate our p-value. Our p-value, we're going to multiply times 2 because we have two tails in the distribution. And we're going to set it up as 1 minus our norm.s.dis distribution of the absolute value of B27, which was our z calculation. Since our z calculation could be positive or negative, since it's two-tailed, we're going to take the absolute value of that. So it's always going to fall on the right half of the distribution, which is why we're subtracting it from 1. that gives us one side of our distribution for our p-value, which is why we multiply it times 2. And in this case, we have a p-value of 0.0264, which is also less than our 0.05 value. So we can say with a level of confidence that we should reject the null hypothesis.